Angular momentum is a pretty powerful concept, and it's related to linear momentum. Let's see where we get that from. If we remember, our linear momentum, P, was equal to mv. Here we have an angular momentum that's defined in terms of our linear momentum as L. This is a lowercase l, that's equal to r cross p. So we take our hand and put it in the direction of the r vector, and then curl it towards the p vector, and that gives us the direction of our L vector, which is that angular momentum. You can remember it's L for angular momentum because angular. Does that help? In any case, we have L is r cross p, which is rp sine theta. Newton's second law then, written for angular momentum, is going to be that the sums of the torques are equal to dl dt. For a system of particles, we end up having the total system of particles will have a total angular momentum that's equal to the sum of the angular momentum for each individual particle. So we basically just add up all of those angular momentums of each particle, and we get our total system angular momentum. That's for discrete particles. For a continuous rigid body, we can derive this relationship that I'm explicitly not doing right here, but is kind of neat to see. I recommend you check it out, where we can show that the angular momentum of a rigid body is equal to I omega. Now let's try and use that relationship to do some calculations. So remember, for a particle, our angular momentum is r cross p, and for a rigid body, it's I omega. All right, let's consider this robot arm. We have a robot arm on the Mars rover, something like Curiosity, that's trying to pick something up. We have some information about how it's moving, and I'm going to note as I read this that we have an omega that's equal to 0.1 pi radians per second. That's the angular velocity that our arm's moving with. It rotates and picks up a Mars rock with a mass of 1.5 kilograms. And now we want to know what's the angular momentum of the robot arm by itself about the axis of rotation after 0.1 seconds when the arm has stopped accelerating. All right. I'm going to draw a diagram of this arm, and hopefully this will help. Here we've got an arm, and then we have at the end of the arm our little grabber dude, where the mass of those forceps that grab things are 1 kilogram. The mass of the robot arm here is 2 kilograms. And we have an axis of rotation down here that we're rotating about. We'll also have our length of our robot arm that's given as 1 meter long, is the distance from there up to the forceps. And I want to know the angular momentum of the robot arm. All right, for the angular momentum of a rigid body like this, my angular momentum is going to be I omega. I need to know my total I, and then I can multiply it by this omega, and we should get our angular momentum. So all I really need to do is find I. My I will be a combination of these two things. It will be the I from the forceps plus the I from the robot arm. From the forceps, let's see if we can do this. The I for the forceps, when we're considering this moment of inertia about the axis of rotation here, we'll treat it as a point mass with that mass of the forceps times the distance that it takes to get to where the forceps are squared. That's 1 kilograms worth of weight times that 1 meter arm, which gives us 1 kilogram meter squared worth of moment of inertia. Now for the robot arm, It's going to be based on this long, skinny thing. We'll look that up and see that this looks like a long rod that in my chart seems something like 1/3 mass times its length squared when we're rotating about at the very end of this thing. We'll plug in our values for this and successfully transcribe 3 to the next line. We have a mass of 2 kilograms, a length of 1 meter, which leaves us with 2/3 of a kilogram meter squared worth of inertia coming from our robot arm itself. We'll add those together, and we get 1 plus 2/3 with units of kilogram meter squared for a total of 1.67 or 1.666, repeating, kilogram meter squared, which we can then plug into our moment of inertia. We plug the moment of inertia into our angular momentum, 1.67 kilogram meter squared, times our angular velocity, 0.1 pi radians per second, leaving us with 0.52. Units on this are kilogram meter squared per second. That's the units of angular momentum. Kilogram meter squared per second.